Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Portantex with Alex Burlack. We're going to talk today about improving system quality and performance. Alex, as you get designs out into the real world and they start looking at these systems operating under real workloads, what sort of problems does that bring up?
So that's a very good question. And in order to solve the problems of workload that's running in a real system in functional mode, we actually need to take a step back and to ensure this functional work during the test of the system. We need to understand what is the performance limiters, whether there is a quality issues that are coming from the assembly of the chip into the system, for example, power delivery issue, even aspects like heatsink issues, characterization of how the functional workloads correlates back to different tests happening in the prior test stages. And of course, also there is the optimization of the performance of the system that can be fine-tuned during the system test before it's being delivered to the real world applications.
Let's take a closer look.
Sure.
Alex, what are we looking at?
So what we're looking here is basically a method of optimizing the operational voltage of the system in order to save power later on in the field. Today, during the life cycle of the chip, in terms of the different test stages, the VDD min, which is the minimum voltage that the chip can still operate, usually determined on ATE. Now, with the visibility that Portantex providing, with the timing margin that can be measured in a parametric manner from within the chip, we can understand how close we are to a failure. And in that way, when the chip is actually assembled into the system, and the system is being run during the functional workload, something that is mimicking a real situation, we can quantify the timing margin and understand if we can push or can lower the voltage even further to reduce or save more power. And that's what you see here. The x-axis is the voltage, the y-axis is the timing margin. So this will be the initial point from the ATE test stage that happened before the system test. We can see that in reality there is enough margin to even further reduce down the voltage.
So really what's happening here is a lot of these chips that are being made for data centers and even for mobile applications, automotive, they're all very customized, right? And so the workloads that are going to run on them are very customized. You need to be able to customize everything else that goes with that to make sure it's going to work.
Correct. So there is also the workload question that are highly customized and change from segment to segment, from data center to mobile, etc., the duration of the workload, etc. But there is also the customization is done by taking a chip and assembling it into the system. Now every system is different, and therefore there is the need to actually to fine-tune and to be able to find the most optimal voltage point for this combination of chip on this specific system. By looking in this and what's happening inside the chip, this is the major advantage that can be done with this type of technology.
And it's not just the workload in terms of what they're trying to do, it's also how long they're run too, right? So a lot of these AI systems, for example, are utilized much more heavily than what we've been seen in the past.
Correct. That's why there are two, the way we look at it, or it's two-phase basically. One is that important to do the fine-tunings and both find quality-related issues during the system test in order to actually enable a reliable system running long-term in terms of long workloads and training mechanisms, etc., and not having a failure in the middle of a long training session for a big AI model. So it's important to have this optimization. It's important to utilize this visibility to detect any defects or any quality-related issues, and later on continue to monitoring this aspect continuously also in the field when the system is deployed in a real data center or mobile, etc.
If you think about AI algorithms, though, they're rolling out at a very fast pace. So what you have today may be obsolete in another week or two. It may be replaced by something else. Is there enough flexibility built into this so that you can actually change what you're looking at as you go along to match the workload?
Yeah, we are not relying on the workload can change, so there is no dependency in terms of what we are measuring inside the chip. we are agnostic to the workload itself, so it's working in a continuous mode. While any type of workload can run, there is no need to kind of change or to put the chip and system to any special test mode. So in that sense, any changes in the workload, it doesn't matter. We are continue monitor that and provide the visibility and alerts to identify any kind of issues.
How about things like accelerated aging, which is one of the problems that you typically run into as these things are in use in data centers or wherever it happens to be for a number of years?
Yeah, so that's a very valid point, and this timing margin that you see here, this is during the system test we measure the timing margin at time zero, but when the chip is running actually in the field for longer time frames, we continue monitoring this timing margin and can quantify actually the degradation on the actual logic paths that is doing the actual functional mission of the chip and alert on this type of degradation or other drivers that can cause a failure of the chip.
Because really what you're doing here is testing over time, right? You're testing at time zero. You're also testing years later. You need to be able to understand what's going on here.
Correct. Actually, we start during AT phase, then we provide visibility during the measurement and monitoring during the system test, and later on continuously measuring while the chip is deployed in field. So we cover the entire time frame of the life cycle of the chip.
So what you're really doing here is marrying the workload to the test, right? You're actually customizing both of those.
So what we can provide is the comparison with our monitors, the comparison of timing margin while a functional workload is running on the system versus a timing margin when a structural test like ATPG at speed is running on the AT. That kind of comparison, which is apples to apples, measured in at the same locations inside the chip, can enable the fine-tune of the ATPG tests or the functional workload to actually to create the right visibility in that sense in terms of not overkilling and not underkilling. So the ATPG will better mimic the functional workload when this is running. So this type of comparison is very important during characterization phase and can be utilized to optimize also ATPG patterns.
How much extra time does this add into the test process? There's already a number of test insertions that are going on inside any fab at this point for different layers that are going into these advanced chips. How does this affect us?
So it does not affect because, for example, again, usually these tests are already running. The added layer that we provide is actually a parametric visibility of what's happening inside the chip while these tests running either on ATE or on the system itself in terms of functional workload as well. This is something that is running. However, there is not a good way to quantify parametric-wise. It's only a pass or fail. And this provides a color to the results.
You're also pretty much fine-tuning this system, right, at a level it's never been fine-tuned before.
Yeah, so what we see here in the plot is the capability to basically, based on the timing margin that is measured inside the chip, to optimize the voltage that the system can run. So instead of running at higher voltage, we can see that if we will reduce even further the voltage, there is still enough timing margin from within the chip while it's assembled onto the system, and that enables basically to cut off or reduce power and save power when for this specific system. This is done for every system, and in that way the average power during in-field operation is reduced significantly. We're talking about multiple percents that can be saved in that way.
So are you always preparing for worst case here?
So we will provide the visibility under the functional workload that the customer is running. Usually it's a combination of worst case scenario versus other types of workload that can happen. Eventually the fine tuning will ensure in terms of robustness. It will be robust enough to withhold within the in-field monitoring, within in-field operation. Saying that, also if there is a situation that later on, when the system is operating in the field, if there is new workloads that are coming into the game, we were able also to alert of a situation that the margin is low, and in that way to provide the visibility to take some action to recover from these kind of scenarios.
What about quality? That's always been a big issue in advanced designs because you are dealing with so many different layers and chiplets and everything else.
Yeah, so the layer of quality that we are adding here on specifically on the system side is using the chip as a monitor for the entire system. And the monitors within the chip can indicate on issues related to the perimeter. Aspects like power delivery, aspects like heatsink, like clock source, capacitors, etc. Now, this combination of the visibility that we provide, we're able to detect abnormal behavior of a system. And the way we are doing that is that in the characterization phase, we are creating some baseline behavior across many systems, creating a model that will detect abnormal systems that are running after that. And in that way, we can flag or outlier systems that actually one of these parameters is behaving not as expected. And in that way, improve the quality and screen this system in order so it will not propagate to the in-field operation.
In the past, most people thought, oh, known good die, that's all we really need to understand. But it's more than that, right? It's known good die in the system as it's already packaged.
Exactly. So it's a packaged chip assembled into the system, and now this is the real thing. Everything that happened before is very important, but this is what really going to operate in the data center, in the phone, in the car, etc. And therefore, it's important to have the right parametric visibility and to ensure that this exact entity is working as expected.
In order to make this work, you have to be part of an ecosystem that's very tightly developed here, right? So you have to be working with the ATE guys as well as the fabs and everybody else, all the way from the design all the way up, right?
So we start in the design phase with the understanding what is the chip is intended to, what is trying to be achieved with our technology, and then we are working with the customer to integrate the agents in the right way to ensure that eventually the value that is required will be achieved. We have tools to do that. We provide the tools for the integration. And later on, when the chip is fabbing out and coming back from the fab, we are ready with all the post-silicon aspects and activities to ensure that all characterization steps eventually are being done. We provide the relevant software that is able to actually create the different types of models, analytics, in-field related applications.
What have you heard back from the customers? Are things running more smoothly? Are you able to understand what's going on in the chip, and does it really help prolong its lifespan?
We see a very good feedback both from bring-up aspect, how it speeds up the bring-up process. Then later on, when you move to high volume manufacturing, either in chip or system level, improvement in terms of DPPM reduction and quality improvement. And beyond that, the things related to in-field aspects like power reduction over time or reliability monitoring in the field as well. So these components is also something that is helping the customers under these segments as well.
Alex Burlak, thanks for a great explanation.
Thank you.